Hello, this is Dave Slopsma from Dimensional Consulting. Today I'm going to tell you about the new Stacks Wizard. The Stacks Wizard is a tool that prompts the user through the thought process required when creating a one-dimensional or two-column stack. The previous version of the Stacks Wizard was written in standalone Visual Basic. The new version of the Stacks Wizard is in Excel with Visual Basic programming. The new version of the Stacks Wizard is vastly more user-friendly than the previous version. This video is a demonstration of how to use the new Stacks Wizard. In order to understand the Stacks Wizard, you have to understand the stack form. Here's our stack form. This is our standard stack form for the two-column method. We'll go through the various columns. First of all, we have to keep track of what part we're in the stack, especially if we do multi-part stacks. Then we have the to from column. This is where you keep track of your stack path. This is extremely important to pay close attention to because later you're going to need this to figure out how you did the stack and whether or not you missed anything. Now in this particular version of the stack form, I have the to from column just all in one. In the new Stacks Wizard, we're going to have one column for to and another column for from. Then we have the name of the tolerance. What kind of tolerance do we have? Do we have a coordinate tolerance? Is it a touch point? Is it a tolerance of position, a profile, a runout? And then we have the column where we'll have the max stack and the column where we'll have the min stack. Those are the two most important columns. This is where we get the name two-column method because what we do in this method is make sure we put the right numbers in these two columns. And then one column gives you the max, the other column gives you the min. Then we have the tolerance column that's mostly used as an arithmetic check. We won't pay very much attention to this, but we've included it in our stack form anyway. And then finally down here we have the result for our max stack, and here we have the result for our min stack. So the Stacks Wizard helps us fill out this form. There are a lot of rules involved with filling out the form, and the Stacks Wizard is going to help us keep track of those rules. It's going to prompt us for the information that it needs, and then it's going to fill out the form for the most part for us, and then do the arithmetic and give us hopefully the right answer. And it'll give us the right answer if we put the right information into it. So let's take a look at the Stacks Wizard. This is the new Stacks Wizard. You can see it is an Excel spreadsheet. The way the Stacks Wizard is set up, you fill in the yellow cells and it fills in the gray cells. So you can see there's fairly little that you have to fill in. So this has an example stack that's in it. And what we're going to do with the Stacks Wizard, we'll start out filling in the yellow cells, and then when we get to this point where we're going to put in our tolerance, we're going to hit one of these tolerance buttons, and then that's going to prompt us for the rest of the information we need for doing our stack. Okay, so that's a brief introduction, come back to it. So let's take a look at a stack. So here's a very simple stack. In this stack, we want to look at what's the max and min distance from the top of the rectangle to the bottom of the square. So our stack path is going to start at the top of the rectangle. It's going to go down to the bottom of the rectangle to the bottom of the part, and then the bottom of the part up to the bottom of the square. You have to understand stack paths. You need to be able to figure out your stack path before you even start with doing your stack or using the Stack Wizard. The Stack Wizard assumes that you can figure out a stack path, and it helps you fill in the stack form based on the stack path. So in this case, we would start out with line 1 going from the top of the rectangle to the bottom of the rectangle. It's a coordinate tolerance, and with our stack form, we have this plus max minus min plus min minus max. And that means if you're going in a negative direction, you're going to put the min absolute value in this column. If you're going to go in the negative direction, you're going to put the max absolute value in this column. If we were going in a positive direction, we would put the max value in this column and the min value in this column. And of course, and this is something you have to understand from just knowing how to do stacks, is that a positive direction is going to the right or going up. A negative direction is going to the left or going down. In this case, we're going down. We're going in a negative direction. Hence, we put the min absolute value in the left column. We put the max absolute value in the right column. And in this column, we just have the difference between the max and the min. So that was step one. With step two, we're going from the bottom of the rectangle to the bottom of the part. Again, it's a coordinate tolerance. We're going in a negative direction. So we put the min absolute value in the left, the max absolute value in the right, and there's our difference. Third step, we're going from the bottom of the part up to the bottom of the square. So now we're going in a positive direction. So we're going to put the max value of 16 in the left column and the min value of 14 in the right column, and the difference is 2. We've gotten through our whole stack path now. So we add up the numbers, and our max distance then is 11.15, and our min distance is 8.85, and the difference is 2.3. So that's how you do this manually. If you had a piece of paper, or if you just made yourself a quick Excel spreadsheet, you just manually enter the values and put in the numbers. You have to keep track of what goes in which column. Well, let's take a look at how we would do this with the stacks wizard.
All right, so as we recall, we only fill in the yellow cells. So we start out, well, what's the name of the part? We only have one part in the stack, so it doesn't really matter too much. So we'll just put part in there. Doesn't matter. Then we have our from and our to. Well, our first from is we're going from the top of that rectangle to the bottom of the rectangle. Notice that as soon as I get out of the cell, it automatically fills in this one because whatever is in here has to go in here. That way we know we have not left any holes in our stack, no missing links in the chain. But now to fill in the rest of this form, we go over here to this little tolerance button. Okay, here's where we're going to fill in our tolerance. And this gives us all the choices of the kinds of tolerances that we might have. Is it a basic dimension? Is it a touch point? Is it a coordinate tolerance? Is it form on a surface? Is it runout or concentricity or symmetry? Is it going halfway through a feature size? Is it a profile tolerance? Is it a tolerance of position? Well, in our case, we had a coordinate tolerance. So we poke on there. Now we get this option, either normal or LMC and virtual condition. This is a very special case, which we'll see later on in the video. Almost all the time you have just your normal coordinate tolerance. Then it asks you, well, is your stack going in a positive direction or in a negative direction? Our stack in this particular step was going in a negative direction. And then was your tolerance specified max min, or was it specified plus minus? We had a max min. So then it says, well, you're going to have to fill in your max value and your min value. So we go back over here to our stack. We say, what was our max value and our min value? We had a max of 2.55, a min of 2.45. We'll fill that in. Our max of 2.55, our min of 2.45, and we hit apply. So now this knows we're going in a negative direction, so it's going to put the min absolute value in the left column. It's going to put the max absolute value in the right column, and it does the math for our total tolerance. Well, now it says, okay, you're in this part called part. You're at the bottom of the rectangle. Where are you going to go next? As we recall, the next step in our stack is to go to the bottom of the part. And once again, tolerance. Again, we've got a coordinate tolerance. It's just a normal one in a negative direction. We've got a max min dimension. We go back here to find out what's our max and min. There's a max 2.6, a min 2.4. Okay. a max 2.6, min 2.4, apply, and again it fills in these columns. It says, okay, now you're at the bottom of the part, where do you go next? Well, we go up to the bottom of the square. Again, tolerance. Once again, we have a coordinate tolerance. It's a normal one. Now we're going in a positive direction. Again, we've got a max-min dimension. What was the max-min? Max 16, min 14. Max 16, min 14, apply. Now notice since we're going in a positive direction, it puts the max value in the left column, the min value in the right column. And our stack is done. We can scroll down to the bottom to see that our max is 11.15, our min is 8.85. And that's all there is to doing it with the stacks wizard. Well, let's go on and look at the next stack. The next stack involves runout. We've got a series of cylinders here, and we want to look at the max and min distance between the bottom of this cylinder and the bottom of this cylinder. So our stack path is going to go bottom of this cylinder to the center of that cylinder, center of this cylinder to datum A as governed by this runout tolerance, datum A to the center of this cylinder as governed by this runout tolerance, and center of this cylinder to the bottom of the cylinder. So let's see what that looks like on the stack form. Bottom of the intermediate diameter to the center of the intermediate diameter, positive direction, going halfway through the 15.1 to 15.5. Always kind of a pain to divide by 2. So max 7.75, min 7.55. And then from the center of the intermediate diameter, we go to datum A using this runout. With runout, you put half in each column, positive in the left, negative in the right. From datum A, we go to the center of the smallest diameter using this runout, half in each column, positive in the left, negative in the right. And from the center of this diameter down to the bottom of this diameter, going halfway through feature size again, halfway through 10.1 to 10.5 is 5.05 and 5.25. Since it's in the negative direction, we're going to put the min absolute value in the left and the max absolute value in the right. And we get our answer, max 2.9, min 2.1. So once again, let's see how to do that with the stacks wizard. First thing we're going to do is erase our previous stack. Now, since this is an Excel spreadsheet, if you're doing this stack for some production parts, you would save it off and save it with some name that you recognize because it's just an Excel spreadsheet. You can save it as you can any other Excel spreadsheet. So we'll go up here and clear our form. Okay, again, we're in a single part stack, so it doesn't matter. Just put part. And we're going from the bottom of the intermediate diameter to the center of the intermediate diameter. And we go over here to tolerance. And we're going halfway through a feature size. Remember, I said it's always kind of a pain to divide by 2. So just to make it easier, I wanted to be able to input the numbers right off the drawing. So we go halfway through feature size. Again, it's just a normal situation. Our stack is going in a positive direction for that step. And we've got a max min tolerance. So it wants to know what's the max diameter and the min diameter for that step. So let's take a look. We've got our max diameter is 15.5, our min diameter is 15.1. Our max 15.5 and our min 15.1. Hit apply. And it has done the math. Divide by 2. Notice it's going in a positive direction, so it puts the max in the left and the min in the right. So now we're at the center of our intermediate diameter. We need to go from there to datum A. And we're doing that with a runout tolerance. Go here to runout or concentricity or symmetry. Well, we've got a runout. And we can just input the runout value. We have to remember what it was. Runout was 0.2. 0.2. Apply. Puts half in each column, positive in the left, negative in the right. Okay, now you're at datum A. Where are you going to go? We're going from there to the center of the smallest diameter. And once again, we're getting there with a runout. And let's just double check. Runout of 0.2. Once again, half in each column, positive in the left, negative in the right. While we're at the center of our smallest diameter, we need to go to the bottom of the smallest diameter. Our tolerance, going halfway through feature size. This time we're going in a negative direction. Max min value. Look at what that is. Max 10.5, min 10.1. Once again, it does the math to divide by 2. Since it's going in a negative direction, it puts the min in the left, the max in the right, and now gives us our value, max 2.9, min 2.1. All right, let's look at another stack. Now here's where we get into adjacent and offset. We've got these form controls on a surface. So in this stack, we're looking for what's the max possible gap between this surface and this surface. Well, the surface on the blue part is controlled by this parallelism. That's controlling the form of the surface on the blue part. And the surface of the, what it claims to be as a green part, although it doesn't look green to me. But anyway, the surface of this part is controlled by this flatness. So to get the max gap, we're going to start out in the blue part, and we're going to go from the worst case form error up to the nominal, or the touch point, with our parallelism of 0.3. And since we're going in a positive direction, we're going to put the max in the left column, and it would be 0 in the right column. And we have our touch point between the blue and the green, 0. And then we go from our touch point up to the worst case form error in the green. That's controlled by the flatness. We're going to put our max flatness value of 0.15 in the left column, 0 in the right column. And we get our max 0.45 gap, min gap 0. And that's all there is to the stack. Well, let's see how we would do this with the stacks wizard. Again, clear the form. Now it does matter a lot which part we're in. And so we're starting out in the blue. And we're going from the worst case parallelism error to the touch point. So we say tolerance. And we have form on a surface. And it says now, is this an adjacent or an offset? Well, this is adjacent. It says, are you going in a positive direction or a negative direction? We're going in a positive direction. So that's okay. What's the form tolerance? Well, what is the form tolerance? It's 0.3, because our parallelism is our form tolerance. So we put 0.3 there, apply, and it knows put the 0.3 in the left column, 0 in the right column. Alrighty, now we have to change parts. We're at the touch point on our blue part. We're going to go into the green part, or what claims to be the green part, and we're going to go to the touch point in that part. We go tolerance. It says, oh, touch point. It says, you're in the blue part now. Where are you going to go? Which part are you going to go into? Well, we're going to go into the green part. Apply. It says, okay, we've got a touch point, 0 distance, 0 tolerance, and it's going from the blue to the green. Now that we're in the green, we're going to go from the touch point to the max flatness error. And let's take a look at what that is. Well, first we go to tolerance. We've got form on a surface again, adjacent, positive direction, and what's our form tolerance? It is 0.15. So we fill that in, 0.15, and it knows to put the 0.15 in the left column, 0 in the right column, and our stack is done. Max gap is 0.45, min is 0. Right, let's look at a different kind of stack again. Here we've got form applied to a surface with an offset because we're looking at what's the distance from this part of this surface up to the top here. So being a vertical stack, we're going to start at the bottom of our stack, which is down here. And we have to acknowledge that we could be going from this point up here down to the nominal, or from this point down here up to the nominal. In either case, we could be going down by 0.3 or we could be going up by 0.3. That's the way form applied to a surface when you have an offset situation works. Therefore, in the first step of our stack, we're going to put our entire 0.3 in both columns, positive in the left and negative in the right. That brings us to the touch point. So we're going to touch between the blue and the green. Then we're going from the touch point up to the top of the green. Max 18.1, min 17.9, and we get our answer, max 18.4, min 17.6. So let's see how we do this with the stacks wizard. Clear our form, starting out once again in the green. Where are we? We're in the blue. Okay. We'll start off in the blue. And we're going to go from the worst case form error to our touch point. Over here to tolerance. We have form on a surface. In this case, we have offset. It wants to know what's our form tolerance. Let's take a look. It's 0.3. Go back here and enter that. 0.3. And it knows to put the entire 0.3 in both columns, positive in the left, negative in the right. Okay, from our touch point on our blue, we need to go to the touch point on the green. Touch, going from the blue to the green. Apply, and we have touch point 0 going from the blue to the green. We're going from the touch point on the green now to the top of the green. And if we recall, that is a coordinate tolerance. It's a normal one. It's in a positive direction. It's max min. Let's just verify what it is. Max 18.1, min 17.9. Max 18.1, min 17.9. Apply. And it knows to put the max in the left, the min in the right. And we get our answer, max 18.4, min 17.6. Well, let's look at another kind of a stack. Now we're into tolerance of position. We'll start out easy. First, regardless feature size, and it's regardless material boundary. In this case, there'd be no shift anyway, because we've got our two tolerances of position, they're a simultaneous requirement. But anyway, easy RFS. So what are we doing? We're looking at going from the bottom of this diameter to the bottom of this diameter. So we're going to have to start at the bottom of our intermediate size diameter, go to the center actual worst case position of our intermediate diameter, center worst case position to center true position with a position, bonus, and shift, and then center true position to datum A-B. Over here we go from datum A-B to the center true position of the small diameter, center true position of the small diameter to actual worst case position of the small diameter, position, bonus, and shift, and an actual worst case of the small diameter to the bottom of the small diameter. So come down here, step 1, center the intermediate diameter, bottom of the intermediate diameter, the center of the intermediate diameter, actual worst case, positive direction, going halfway through the 15.8 to 16.2, that's max 18.1, min 7.9. Then we go center of the intermediate diameter, actual worst case, to the center of the intermediate diameter true, with our tolerance of position of 0.3, half in each column, positive in the left, negative in the right, because that's how you handle tolerance of position in the two-column stack form. Well, we said we're RFS, and there's no shift, so bonus is 0, shift is 0. So now we're at the center of our intermediate diameter true position. We need to go from there to datum A. Well, in a perfect world, they'd be right on top of each other, so there's an implied basic 0 between the center true position of the intermediate diameter, datum A-B. Then we go from datum A-B to the center true position of the small diameter, another implied basic 0. And then center true position of the small diameter to center worst case, actual of the small diameter, with our tolerance of position. Tolerance of position is 0.2, half in each column, positive in the left, negative in the right. And then we've got 0 bonus, 0 shift. And finally, we go from the center of the small diameter actual worst case to the bottom of the small diameter, going halfway through the 9.9 to 10.1. That's 4.95 to 5.05. Going in a negative direction, so we put the min absolute value in the left, the max absolute value in the right. And we get our answer of max 3.4, min 2.6. All right, let's look at how to do this with Stacks Wizard. Clear our form from our last stack. Now we're all in the same part again, so we don't have to worry too much about what to call it. Remember, we're starting out at the bottom of the intermediate diameter, and we're going to the center of the intermediate diameter, actual worst case. Our tolerance, we're going halfway through a feature size. It's a normal situation, going in a positive direction. Got a max min diameter called out. Check the max and min diameter. It's a max 16.2, min 15.8. Max 16.2, min 15.8. Hit apply, and it knows to divide by 2 and put the max in the left, min in the right. So we're at the center of our intermediate diameter actual, worst case. From there we have to go to the center of our intermediate diameter true position. So come down here to our tolerance, and we have a tolerance of position. So we have to think through now. For the considered feature, is it RFS or MMC or LMC? Well, it's RFS. For our datum feature, is it either regardless of material boundary or a simultaneous requirement, or is it MMB or is it LMB? Well, it's regardless of material boundary and it's a simultaneous requirement, so we just leave them both like that. We check out what the values are for our position tolerance, and it is 0.3. Come down here and enter 0.3. And it knows to take the tolerance of position, put half in each column, positive in the left, negative in the right. It knows that bonus is 0 and shift is 0. And it says, okay, you are at your center of your intermediate diameter true position. Where are you going to go from there? Well, we're going to go to datum A-B. B. Go to our tolerance. And remember we said that that was going to be a basic zero, an implied basic zero. So basic doesn't really matter so much as if it's positive direction, positive or negative, as long as it's zero. Apply. Now we're at datum A-B. We need to go to the center of the small diameter. True. And that is another basic implied zero. So we're at the center of our small diameter true. We go to the center of the small diameter actual worst case. And that once again is governed by a tolerance of position. It's going to be RFS. For the considered feature, it's going to be regarded as material boundary. And we'll double check on the value of it. And that's going to be a 0.2 tolerance of position. So we go back and enter that. Apply. Takes the tolerance of position, half in each column, positive in the left, negative in the right. It knows that bonus is 0 and shift is 0. And it says now you're at your center of your small diameter actual worst case position. Where are you going to go from there? We're going to go to the center. No, we're going to go to the bottom of our small diameter. Hit our tolerance button. We know we're going to go halfway through feature size. It's a normal one going in a negative direction. It's going to be a max min. Check what the max and min are. Max is 10.1, min is 9.9. Max 10.1 and the min is 9.9. And it divides it by 2, puts the min in the left column, the max in the right column, and we'll get our answer of max 4.75, min 1.25. All right, let's look at the next step. Things are going to get a little bit more interesting because now we're going to do tolerance of position with MMC. We have our same part, our same stack path, but now we've got the MMC modifier here and the MMC modifier here. So we're going to start again from the bottom of the intermediate diameter and go to the center, actual worst case, max 8.1, min 7.9. We're going to go from the center of that diameter actual worst case to the true position of that center with our tolerance of position of 0.3, half in each column, positive in the left, negative in the right. We're going to now have bonus tolerance. Now, as we recall, if we've taken the stacks class, that when you have bonus tolerance, you have to look at your stack path. And look at where you went through the considered feature size. This is our considered feature size, or it's feature size that we're measuring. We went through the radius of our considered feature size, and there's a rule that says if you're going through the radius of a considered feature size, then you're going to put your max radial bonus in the column where you went through the LMC radius of your considered feature size. You're going to put 0 bonus in the column where you went through the MMC radius of your considered feature size. Because there's no bonus at MMC, you get your max bonus at LMC. So we look back here, this is where we went through the radius of our considered feature size. It's an external feature size, so we went through the MMC radius in this column where we went through our 8.1 radius, so we put 0 bonus there. We went through the LMC radius in this column where we have the smaller number, the 7.9. So we're going to put our max radial bonus there. Remember, you calculate the max radial bonus from the size tolerance. And the size tolerance is 0.4 on a diameter basis, but we need radial bonus, so we divide that by 2. So we have 0.2 radial bonus in the column where we went through the LMC radius of our considered feature. And since it's in the right column, it's negative because tolerances are always positive in the left column, negative in the right column. All right, now we know our shift is going to be 0. So this brings us to the true position of the center of the intermediate diameter. We go from there to datum A-B, the implied basic zero. From datum A-B to the center true position of our small diameter, it's another implied basic zero. Center true position of our small diameter to the worst case position of our small diameter is governed by this tolerance of position of 0.2, half in each column, positive in the left, negative in the right. And this says we're going to have bonus, but in order to calculate the bonus, we're going to have to do step J. Well, we're not there yet. So we're going to have to skip our bonus for now. We're going to have to acknowledge that we've got no shift. We're going to have to do step J, going halfway through the 9.9 to 10.1. So that's 4.95, 5.05. And then this is the information we're going to use for calculating our bonus for this tolerance of position. So we're going to take a look at this. This is an external feature of size. So the big number is where we went through the MMC radius of our considered feature size. So we're going to put 0 bonus in that column. This is the small number where we went through the LMC radius of our considered feature size. We're going to put our max radial bonus in this column. We're going to calculate our bonus from the size tolerance. Size tolerance is 0.2 on a diameter basis. We need it radial, so divide that by 2, so that's 0.1. So we have our 0.1 bonus. We put it in the left column because that's where we went through the LMC radius of our considered feature size. And since it's in the left column, it's positive. And so now we can just add things up, get our answer, max 3.5, min 2.4. Now this is where the stacks wizard really starts to save you some frustration, a lot of work, a lot of thinking through things. Let's see how we do this stack with the stacks wizard. Okay, we're going to clear our form. Once again, we're all within the same part. We're going to start out easy, going from the bottom of the intermediate diameter to the center of the intermediate diameter actual worst case. Our tolerance button. So that's just halfway through feature size. It's a normal one. Positive direction. Max min. Let's double check the max and min. So max 16.2, min 15.8. So max 16.2, min 15.8. Apply. We've done this before. Max 8.1, min 7.9. Go from our center intermediate diameter actual worst case to the center of the intermediate diameter true position. Hit our tolerance button. Have a tolerance of position. Now our datum feature is still, it's RMB, and it's a simultaneous requirement. So we just leave that as is. But now for our considered feature, say, well, we reference it, called it out MMC. Well, then there's some things we need to think through. We're going to have to take a good look at our stack path, because it wants to know, when you go through that considered feature, are you just going through the center of it? Are you going through the radius of it in a positive direction, or are you going through the radius of it in a negative direction? Well, let's look. Our first step went through the radius of our considered feature in a positive direction. So we go through the radius of the considered feature in a positive direction. Our considered feature was an external feature size, and the size was specified max min. Well, it wants to know what's our tolerance of position, what's our max and our min for our considered feature size. Our tolerance of position is 0.3, our max and min are 16.2 and 15.8. Tolerance of position 0.3, max 16.2, min 15.8, and apply. Based on the questions that it asked us, based on all those little things we clicked on, it knows to put tolerance of position of 0.3, half in each column, positive in the left, negative in the right. It knows to put 0 bonus in the left column, 0.2 in the right, and being negative in the right column, and it knows that shift is 0. Well, that's a whole lot less worrying and thinking through things and trying to figure out where things go than it was when we did this manually. All right, now we're at the center of your intermediate diameter true position. We're going to go from there to datum A-B. And as we recall, that is basic 0, an implied basic 0. And then from datum A-B, we go to the center of the small diameter true, and that is another implied basic 0. And then from the center of the small diameter true, we're going to go to the bottom. No, we're going to go to the center of the small diameter actual. Get our tolerance. Once again, we have a tolerance of position. Datum feature is going to be RMB. Considered feature is MMC. And it wants to know how our stack path is going. Well, let's take a look. Our stack path going through that smallest diameter is going in a negative direction. Through the radius in a negative direction. All right, so through the radius of the considered feature in a negative direction. And our considered feature is an external feature size. It's specified max min. So it wants to know what's the tolerance of position on our considered feature, what's the max and min. Let's look. Tolerance of position is 0.2, max is 10.1, min is 9.9. Tolerance of position 0.2, max diameter 10.1, min diameter is 9.9. And based again on all these things that we just answered here, hit apply, and it knows to put tolerance of position half in each column, positive in the left, negative in the right. It knows to put our bonus tolerance positive in the left column, 0 in the right, and shift to 0. Now, last step, going from the center of the small diameter actual to the bottom of the small diameter. That is going halfway through feature of size. And we're going in a negative direction, and it's a max min tolerance. And let's take a look at what the max and the min are. It's a max 10.1, min 9.9. And it does the math for us, fills it all in, adds things up, and says our distance is a max 3.5 and a min 2.4. So that now really saved us a little bit of hassle. And speaking of saving a little bit of hassle, let's take a look at the next step. So let's look at this stack that involves max material condition and max material boundary. And therefore, we're going to have bonus tolerance and datum feature shift. The stack is looking for the maximum distance between the right side of this hole and the left side of this slot. The hole is the datum feature, and the slot is the considered feature. Stack path is going to start at the right side of the hole, go to the center of the hole, which for the purposes of this stack is datum D. Remember, a datum is at actual worst case position and true position at the same time. So we can go right from datum D to the center true position of this slot. Then center true position of the slot to the actual worst case position of the slot using position, bonus, and shift, and then actual worst case of the slot to the left side of the slot will be done. So let's see how this works. First of all, we go right side of the hole to D, going halfway through the 10.1 to 10.5. It's going in a negative direction, so we're going to put the min absolute value on the left and the max absolute value on the right. Then we go from D to the center true position of the slot. It's basic dimension, so we have a positive value in both columns and 0 tolerance. Center true position of the slot to actual worst case position of the slot using the tolerance of position of 0.1, half in each column, positive in the left, negative in the right. And the next step would be bonus, but we can't do our bonus yet until we do step F. We won't have the information for our bonus tolerance until we do step F. So we have to skip over that for now and move on to shift. Now for datum feature shift, we need to use the information associated with the datum feature. And that is the size 10.1 to 10.5 and the tolerance of position of 0.2. Remember that datum feature shift is the looseness between the datum feature and the datum feature simulator. And the datum feature simulator is this max material boundary. Max material boundary then is the largest perfect pin, in this case, that's perpendicular to A, that will always go through the datum feature whenever the datum feature is within spec. Well, that largest boundary that's not going to be violated then by that hole is going to be governed by the size of the datum feature hole and the tolerance of position, because the tolerance of position of 0.2 is going to control the perpendicularity of the hole relative to A and also the spacing of those two holes. So both of those will be relevant to our calculation of what's the largest pin that will always fit through that hole whenever the hole is within spec. And that's going to be equal then to the smallest hole minus the tolerance of position. And so that's 9.9 is our max material boundary. Our max looseness then, which is our max shift, is the largest possible hole minus that max material boundary. So 10.5 minus 9.9 divided by 2 to get it radial, and so that's 0.3 is our max possible datum feature shift. Our min shift is going to be the smallest hole minus that max material boundary. So 10.1 minus the 9.9 divided by 2 to get it radial, and so that's 0.1. So those are the calculations for max and min radial shift. Then we have to decide which column to put those in. Well, according to our rules we have for doing stacks with shift, we have to look at where we went through the datum feature of size in our stack path, and we did that in the first step. And in the left column, where we have the small number here, that's where we went through our MMC radius of our datum feature, and therefore we're going to put our min shift in that column. In the right column, with the larger number, that's where we went through the LMC radius of our datum feature, and therefore we're going to put our max shift in the right column. That's how we calculated our shift. That's how we decided which columns to put them in. And of course, with any tolerance, it's always positive in the left column, negative in the right column. Okay, so now we have our position and our shift. Move on and do step F, going halfway through the slot, so halfway through the 1.9 to 2.1 in the negative direction. And so min absolute value in the left, max absolute value in the right. Now we have the information that we can use to calculate our bonus for our tolerance of position. So we look at where we went through that slot, and in the column where we went through the MMC radius of the slot, here with a small number, we're going to put 0 bonus because there's 0 bonus at MMC. In this column where we went through the LMC radius of the slot, we're going to put our max bonus because we get the max bonus at LMC. Remember, we calculate the bonus from the size tolerance. Size tolerance is 2.1 minus 1.9, so that's 0.2. Divide it by 2 to get it radial. And so our max radial bonus is 0.1. It's in the right column, and therefore it's negative. And with that, we can add up our totals and get our max distance of 1.65 and our min distance of 0.75. Now let's see how we do this with the stacks wizard. We have just one part here again, so we just put part, doesn't matter what it's called. Remember, we started from the right side of the datum hole. We went from there to what, for purposes of this stack, is datum D. So that was going halfway through a feature of size, and it's a normal feature of size. We were going in a negative direction. The specified max min. Let's look at what the max and the min were. And the max was 10.5, the min was 10.1. Hit apply, and it enters our first line. So we're at datum D. We need to go from there to the center of the slot, true. And that's going to be a basic dimension, and it was a basic 7.5. Apply. So it puts our 7.5 in both columns positive with 0 tolerance. Then we have to go from the center of the slot true to the center of the slot actual worst case. And this is where the stacks wizard is really going to help us out in saving all those calculations and figuring out what has to go in what columns, and whether it's positive or negative in a given tolerance. So we go here and we've got tolerance of position, and in this case it is MMC and it is MMB. So let's first take a look at the things that talk about the considered feature, which is the slot. First of all, we have to look at the stack path. How is it going through the considered feature? Well, our stack path is going through the radius of our considered feature in a negative direction. So we're going through the radius of our considered feature in a negative direction. Our considered feature is an internal feature of size, and it's specified max min. All right, now for our datum feature, where's the stack path going? Well, our stack path went through the radius of our datum feature in a negative direction also. So through the radius of the datum feature in a negative direction. It also is an internal feature size, and it's specified max min. Now we have all the things up here that we know we have to fill in. So here we have the information for the considered feature. Down here we have the information for the datum feature. So what's our position tolerance and the max min for our considered feature? Well, we have a tolerance of position of 0.1 and a max of 2.1, min 1.9. So 1.1, 2.1, and 1.9. 0.1, 2.1, 1.9. And then we have to look at what is the same information for our datum feature. For our datum feature, we have a tolerance of position of 0.2, a max diameter of 10.5, and a min diameter of 10.1. So 0.2, 10.5, 10.1. 0.2, 10.5, 10.1. So it has prompted us to think through all the things that we need to consider when we calculate our bonus and calculate our shift, and when we figure out in which column to put the max and min bonus, and which column to put the max and min shift, and whether things are positive or negative. And with all that, we hit our apply, and it fills in our tolerance of position, plus or minus 0.05, 0 in the left column, minus 0.1 in the right column, our shift, positive 0.1 in the left column, negative 0.3 in the right column. So it's dealt with all of that for us without having to go through all the calculations manually. So this is really where the power of the stacks wizard is. So where are we now? We're at the center of the slot, actual worst case position. From there we have to go to the left side of the slot, and that's just going halfway through a feature of size. It's a normal one. It's in a negative direction. It's called out max min. Let's verify the numbers. Max 2.1, min 1.9. And it fills in our final line. And we can scroll down and get our answer of max 1.65, min 0.75. So it makes it just that easy to do position with bonus and shift. Okay, let's move on to a few more stacks. Let's move on to profile of a surface. So here we have a profile of a surface callout, and we want to look at what's the max and min distance between the bottom of the slot and the top of the slot. Now this is an equilateral profile. So when we start out, we have to start out at an actual worst case position, and we have to consider the fact that the actual Worst case position might be above or below the true profile. And we're going to end at an actual worst case position, which also could be either above or below the true profile. So we start out having to go from actual worst case to true profile. With our profile of 0.2, half in each column, positive in the left, negative in the right. Now that we're at true profile, we can go true profile to true profile with our basic dimension of 10. We've got 30 across here, 10 here, 10 here, so there's 10 left for the basic dimension here. That brings us to true profile at the top of the slot. We go from true to actual worst case. Once again with our equal bilateral profile, half in each column, positive in the left, negative in the right. And that completes our stack. So let's look at how to do this with the stacks wizard. Clear our form. I'm going to start out, again, it's all in one part. I'm going to start out from the actual worst case of the bottom of the slot. We're going to go from there to the bottom of the slot true profile. And we're going to use our profile tolerance. We don't have any shift, don't have any MMB, don't have any LMB. So we've got equal bilateral. We just enter our equal bilateral profile tolerance. Let's double check what it is. It's a 0.2. So we just put 0.2, apply, and we're done. It enters half in each column, positive in the left, negative in the right. So we have to go from the bottom of the slot true to the top of the slot true. And that, as we recall, is a basic dimension. And that we did 30 minus 10 minus 10, so that was 10. Apply that. 10 in both columns, no tolerance. Then we go from the top of the slot true to the top of the slot actual, worst case. Once again, using our equal bilateral profile without shift, equal bilateral, and verify again that it is 0.2. And it fills it in for us. Half in each column, positive in the left, negative in the right. And we're done. We have a max 10.2 and a min 9.8. So it's just that quick and easy with equal bilateral profile. Now let's look at equal bilateral profile with datum feature shift, because this can happen. Remember, profile will never have bonus tolerance, but it can have datum feature shift. It has datum feature shift in this kind of situation where you have profile with the datum feature referencing max material boundary. Now this is a stack that kind of exercises a lot of things that we talk about in the stacks class anyway. Because in this stack, it says find the maximum distance surface to surface. It does not say from datum C to the surface. It says surface to surface. And this surface has a flatness tolerance on it. And because of the way you would have to measure this flatness, you would put it up against a flat surface here. Datum C would be this perfectly flat plane that's tangent to the surface. So all the flatness tolerance would end up being unilateral inside of the part. So if we're going to start at our worst case flatness error, we're going to start inside the part, or inside the true profile. We're going to go from there to the left, 0.1, to get to datum C. And then once we're at datum C, we go 15 basic dimension to get to the true position of this hole relative to datum C. True position to actual worst case position using our tolerance of position. And our bonus and shift will be, no, we'll have bonus. We won't have shift. And then this hole kind of changes functions. Instead of being a considered feature size, it changes to being a datum feature because it's a datum feature relative to this surface. So when we go from this datum, this surface true profile, to actual worst case using our profile of the surface and incorporating datum feature shift. So let's see how all this works out. We start out using our flatness tolerance. We go from the worst case surface going just to the left to datum C. So 0 in the left column, minus 0.1 in the right column because we're going just in a negative direction. We go from datum C, basic dimension, to the true position of that left hole, true position of the left hole to the actual worst case position of the left hole using our tolerance of position of 0.2. Half in each column, positive in the left, negative in the right. And then we have to think about bonus tolerance because we have this max material condition modifier. Well, look at our stack path. It goes to the center of our considered feature and from the center of our considered feature off again to the right. It does not go through the radius of our considered feature. It goes through the center only of the considered feature. And therefore we're going to put max bonus in both columns. Calculate the bonus from the size tolerance. Size tolerance is 0.4. Divide it by 2 to get it radial. So we put our max radial bonus of 0.2 in both columns, positive in the left, negative in the right. Now we have planar datums here, no MMB modifiers, and so shift is going to be 0. So up until this point, this hole has been our considered feature. Now it changes roles and becomes our datum feature relative to the surface on the right. So we go from our datum feature to the true profile of the surface on the right with the basic dimension of 45. And then we have to go true profile to actual worst case of the surface on the right with our profile of the surface of 0.3, half in each column, positive in the left, negative in the right. There's not going to be any bonus, never is with profile, but we have datum feature shift, and therefore we are going to have to calculate our max material boundary, which is going to be the largest pin that will always go through this hole whenever this hole is within the spec. The largest pin perpendicular to A that will always go through this hole whenever this hole is within the spec. And therefore we have to include in our calculation the tolerance of position, which controls the perpendicularity of this hole relative to datum A. So our max material boundary is going to be equal to the smallest hole minus the tolerance of position, which controls our perpendicularity, and therefore it's 9.9. Our max shift, and remember we only need max shift because we're going through the center only of this hole, so we're going to put max shift in both columns. Max shift is going to equal the maximum size of the hole, the LMC hole of 10.5, minus our max material boundary of 9.9, divided by 2 to get it radial. So our max radial shift is going to be 0.3. We're going to put that in both columns, positive in the left, negative in the right. And so then we add up our totals, max 60.75, min 59.15. Let's see how to do this with the stacks wizard. Clear our form from our last stack. Once again, we're all in the same part. We're going to start from the worst case form error on the left side of that part, and we're going to go to datum C. And when we do that, we've got form on a surface. And it's the adjacent condition. We're just moving adjacent to the worst case. We're not doing this offset thing. We're going in a negative direction, and our form tolerance is 0.1. And so it is placed 0 in the left column, negative 1 in the right column, and it gets us where we need to be. So now from datum C, we're going to go to true position of that left hole. And that's going to be a basic dimension. And the basic dimension is 15. And there we go. Then we go true position of the left hole to the actual worst case position of the left hole relative to datums ABC. That's going to be a tolerance of position. And our shift is not going to be there. It's regardless of material boundary. But we have an MMC. And if we look at our stack path, recall that our stack path goes through the center only of the considered feature. So we say through center only of considered feature. And then it needs to know do we have a max min or a plus minus. It's max min. And so let's look at what our tolerance of position is and the max and min diameters. Tolerance of position is 0.2 and the max and min diameters are 10.5 and 10.1. So 0.2, 10.5, 10.1, apply, and gives us our position, plus or minus 0.1, our bonus, max radial bonus in each column, plus or minus 0.2, and 0 shift. So now we're at the actual worst case position of that left hole relative to ABC, and now that left hole becomes our datum feature relative to that surface on the right. So we go from there to the true profile of the right surface. And to do that, we have basic dimension. And it's going to be a basic 25 plus 20, so that's 45. So now we're at the true profile of that surface on the right. We have to go from there to the actual worst case of the surface on the right. And remember, that's governed by a profile of a surface. And we have MMB. It's an equal bilateral profile of a surface. And our stack path, if we recall, it went through the center only of the datum feature. The datum feature was an internal feature size, and the datum feature was specified max min. So now we need to go back and look at what's our profile tolerance, what is the tolerance on the datum feature that controlled the orientation of that datum feature, and what's our max and min diameter of our datum feature. Okay, so the profile tolerance here is 0.3, and the tolerance that controlled the orientation of the datum feature relative to datum A is 0.2. Our max and min diameter of the datum feature are 10.5 and 10.1. So let's see if we can remember all of that. Profile tolerance is 0.3. Our orienting tolerance on our datum feature was 0.2. And our max size of the datum feature was 10.5. And the min size was 10.1. Apply. And it gives us our profile. Profile was 0.3, puts half in each column, positive in the left, negative in the right. Calculated our shift. It knew that we needed max radial shift in both columns because we went through the center only of our datum feature. And that's the end of our stack. And we have a max 60.75, min 59.15. Now let's look at a stack with a unilateral profile. Here we have our profile of a surface. It says we have a 0.2 wide tolerance zone, unequally disposed, with 0 of that tolerance zone outside the true profile. Therefore, the entire Tolerance zone is inside the true profile. Now when you do one of these, you always need to draw your tolerance zone. So I've done that here. It's a 0.2 wide tolerance zone, and it's all inside the true profile. You have to draw this in here in order to understand how to do your stack path. And the stack wants to look at the maximum distance from the bottom of the slot to the top of the slot. Remember, with the profile of a surface, we always start at our worst case error, so that's going to be down here inside the part, or inside the true profile. We're going to go from there to the true profile, going to go true to true, and from true up in a positive direction to the worst case error up at the top of the slot. So do that. Start from the bottom of the slot actual to the bottom of the slot true with our profile of the surface. And with unilateral profile, we're going to put the entire 0.2 in the left column because it's positive, and 0 in the right column. And then we go true profile to true profile, our basic 10, and then true profile to the actual worst case again, going in a positive direction, and therefore we put the entire value in the left, 0 in the right, and we get our total of 10.4 max and 10 min. Let's look at how to do this with the stacks wizard. So we start out at the bottom. First of all, we're going to acknowledge that we're in some kind of a part. Start out from the bottom of the slot actual worst case, going to the bottom of the slot true. Go here, get our tolerance. We're in profile. We're without shift. Now we are unequal. And it wants to know how much in the positive direction, how much in the negative direction. Well, let's double check here. We want to go in the positive direction, 0.2. So 0.2 in the positive direction, 0 in the negative direction, and there we are. And then we go true profile to true profile, so top of the slot true. Tolerance is going to be a basic dimension. And let's just verify what that is. It's going to be 10. There we are. Then slot top of slot true to top of slot actual with our unilateral profile once again. Profile, no shift, unequal, and in positive direction once again is going to be 0.2, negative direction is going to be 0, and there we are. And so we get our max 10.4 and our min 10. Just that easy. Let's look at this stack with an irregular feature of size. You don't see these very often, but I do see them more than I would expect. So you need to know how to handle them. Now with this irregular feature size, the irregular feature size is the considered feature. And slot down here is the datum feature. And we're looking for the max and min between the top of the slot and the top of the hexagons. So our stack path is going to start at the top of the slot, going to go to the center of the slot, which is datum B, and then datum B to the center true position of the hexagons, and then true position of the hexagons to the actual worst case position using a position, bonus, and shift. Then actual worst case of the hexagons up to the top, first to the top true, and then to the top actual worst case, because the size and the form of these hexagons is controlled by this profile of the surface. The location is controlled by the tolerance of position. Let's see how we do this. We're going to start out going from the top of the slot down here down to datum B, center of the slot, just halfway through the 6.9 to 7.1. That's easy. Then we have our basic dimension going from B up to the center true position of the hexagons. And we have to go center true position of the hexagons to actual worst case position of the hexagons, while the location is controlled by the tolerance of position. So 0.2 tolerance of position, half in each column, positive in the left and negative in the right. Now we can't do our bonus yet because we need to do steps actually F and G before we can do our bonus. So we're going to skip down here and do our shift. Of course, the MMB modifier says we can have shift. And remember, shift is the looseness between the MMB and the datum feature. Our MMB, since we don't have any GD&T on the datum feature, it's just going to be equal to the MMC size of 6.9. And then our max shift is going to be the largest slot of 7.1 minus 6.9 MMB divided by 2 makes 0.1. And our min shift is going to be the MMB of 6.9 minus the MMC of 6.9, which is 0. So it's a unique thing when you have no GD&T on your datum feature that your min shift is going to be 0. And let's see now where we put the max and min shift. We have to look at where we went through the datum feature in our stack path, and we did that in the top line. Datum feature was an internal feature size, and so we went through the MMC radius of our datum feature in the left column, where we have the small numbers. That's where we put our min shift of 0. We went through the LMC radius of our datum feature in the right column, where we have the large number, and therefore we put our max radial shift of 0.1 in the right column. So that gives us our shift. Now we need to move on to step F, where we go from the center actual worst case of the hexagon up to the top true profile. So that's just a basic dimension. It's half of this 10, so it's 5. Then we have to go true profile to actual worst case profile with our profile of the surface, equal bilateral, 0.3, so half in each column, positive in the left, negative in the right. Now this information is going to give us what we need to know in order to do our bonus. We know our bonus is going to be based on the size tolerance. The size tolerance of the hexagon is actually 0.6 because the hexagon could get 0.3 bigger than its true profile, and it could get 0.3 smaller than its true profile. So the size is 0.6. We want radial bonus, so we take half the size, take the size divided by 2, and so our max radial bonus is going to be 0.3. And then we have to figure out which column it goes in. And remember, we always figure out which column our max bonus is going to go in by looking at where we went through the LMC radius and the MMC radius of our considered feature size. Well, it's a little bit confusing when you have an irregular feature size because your size is controlled by the profile of the surface. So if we look down here, the size of this thing is controlled really by the basic dimension and the profile of the surface. So our max size here is going to be 5 basic plus the 0.5, the radial size. The min radial size is going to be 5 minus 0.15. And therefore, we've gone through the LMC radius in our left column, so that's where we're going to put our max bonus. We've gone through the MMC radius in the right column, so we're going to put our bonus of 0 in the right column, because 5 minus 0.15 was the smallest radius. 5 plus 0.15 was the largest radius. So you have to sit back and think through that a little bit. But you just have to get used to treating an irregular feature size as a regular feature size and figuring out the size from the basic dimensions and the profile of the surface. Add up our totals, get max 32.1, min 31.1. So let's look at how to do this with the stacks wizard. Clear our form, install in one part, and our stack goes from the top of the slot to the center of the slot, which is datum P, and that is going halfway through a feature size. It's a normal one, it's going in a negative direction, and it's specified max min. And the max and min are 7.1 and 6.9. 7.1, 6.9. Okay, that part is easy. We've done that sort of thing before. Then we have to go from the center of our slot, or from datum B, up to the center of the hexagons with the basic dimension, and it's in a positive direction. Let's see what that basic dimension is. That's a basic 30. And now we need to go, forgot to fill in this part. We're going from B to center of hexagon true. All right, click in there, and that says we're at center of hexagon true. We can go from there to the center of the hexagon actual worst case. Okay, go over here to tolerance of position. And we've got MMC and MMB. So let's look at our stack path for the considered feature, the hexagons. Our stack path is going in a positive direction through the radius. So through the radius, positive direction. Those are internal features of size, and they're specified, say, max min. We're going to have to think through this because this is set up as if it were a feature size with a regular size tolerance. Remember, our size is controlled by the profile and the basic dimensions. Let's go down here now and look at the things for our datum feature. Look at our stack path. Our stack path went through the radius of the datum feature in a negative direction. Okay. The radius in a negative direction. Datum feature is an internal feature size. It's specified max min. Okay, now to fill in these things, the position tolerance for the considered feature, max and min sizes of the considered feature, and the datum geometric tolerance, and the max and min sizes for datum feature. So let's first look at the considered feature, the hexagons. Position tolerance is easy. Okay, that's going to be a 0.2. Let's just go ahead and enter that, and then come back and think about the rest. So we need to say the max and the min size of our considered feature. Well, these hexagons, the max size would be the 10 basic dimension plus 0.3. The min size is going to be 10 minus 0.3. So 10.3 max and 9.7 min. 10.3 max, 9.7 min. Okay, now for the datum geometric tolerance, remember there is no geometric tolerance on our datum feature, so that's 0. So we just have to look at what's the max and min size for our datum feature, 7.1 and 6.9. 7.1 and 6.9. Hit apply. And it gives our tolerance of position, half in each column, positive in the left, negative in the right. Calculates our max radial bonus of 0.3, puts it in the left column. Calculates our datum feature shift, 0 in the left column, 0.1 in the right column. 0 in the left column because min shift was equal to 0 because we had no geometric tolerance on our datum feature. Okay, so now we're at the center of our hexagon, actual worst case position. Yes, actual worst case position. We need to go from there to the top at the true profile. And so we choose, well, which of these? Well, remember, hexagon going from the center to the true profile of the top, that's controlled by a basic dimension. Let's take a look. We've got a basic dimension of 10, so going from the center to the top is going to be 5. Okay, then we have to go from true profile to the actual worst case using our profile of a surface. No shift is equal bilateral. And what's our profile of a surface? Is 0.3. And that gets us to the end of our stack. We've got a max 32.1, min 31.1. So this is one that really gets you thinking. But I wanted to make sure I included this because you could encounter it, you need to know how to do it, you need to know how to do it with the stacks wizard. Let's do this one yet. I've been telling you all along that eventually we're going to see what the deal is with the coordinate tolerance, with the LMC, and the virtual condition. So here it is. When you have a feature size, and it has a flatness applied to the feature size, and you have another feature size going into it, it's got another flatness applied to the feature size. You want to know what's the space between the top of the yellow and the top of the slot here in the blue. Well, you can't just do the sizes because the maximum boundary that this yellow part is going to take up is going to be equal to the max size plus the flatness tolerance. And the minimum space within the slot that's going to be allowed for the yellow part to go into is going to be equal to the smallest size minus the flatness tolerance. So what's controlling these stacks, instead of being the MMC and the LMC, it's going to be the virtual condition and the LMC. We're going to incorporate flatness into our calculation and do a virtual condition and LMC in the same line instead of doing like some people will do. They'll do a max and min size and then put the flatness in the separate line. The way I teach it is that we incorporate the flatness into the one line and do a virtual condition in one column, the LMC in the other column. So let's see what we mean by that. So our stack path goes from the top of the yellow to the bottom of the yellow. We touch the bottom of the yellow to the bottom of the slot, go from the bottom of the slot to the top of the slot. So when we go from the top of the yellow to the bottom of the yellow, feature size virtual condition. Going in a negative direction, and so we're going to put the min absolute value on the left, the max absolute value on the right. But the min absolute value, yes, that's going to still be the LMC at 17.9, but the max absolute value that this could be is equal to 18.1 plus the 0.2, so an 18.3. We have our touch point there. And now once again, going from the bottom of the slot to the top of the slot, we have feature size virtual condition. We're going to put virtual condition in one column, the LMC in the other column. We're going to put the max in the left column, min in the right column. The max is going to be the LMC of 20.2. The minimum this could be is going to be the virtual condition of the 19.8 minus 0.3, so it's 19.5. Okay, so let's see how to do that with Stacks Wizard. Clear our form. Now we have two parts, and we're going to start out in the yellow part, and we're going to go from the top to the bottom. And we get our tolerance. It's a coordinate tolerance, but now it's this LMC and virtual condition thing. So it needs to know which direction are you going in. Well, we're going in the negative direction. It's an external feature size. and a specified max min. So it wants to know what's our geometric tolerance on that and what's our max and min value. So our geometric tolerance is going to be 0.2, max and min is 18.1 and 17.9. So 0.2 and 18.1 and 17.9. Apply, and it has put our LMC in the one column and our virtual condition in the other column. And it's labeled it virtual condition coordinate, so it alerts us when we go back over the stack that says, oh yes, this is one of those where we did the LMC and the virtual condition instead of just doing an LMC and MMC. Okay, now we're at the bottom of the yellow. We need to go to the bottom of the slot, and that's changing parts. So we're going to go into, have a touch condition, go into the blue part, and then we go from the bottom of the slot to the top of the slot, once again with a coordinate tolerance, and once again it's going to be the LMC and virtual condition, going in a positive direction. Now it's an internal feature size, specified max min. So let's look at what's our geometric tolerance, our max value and our min value. Geometric tolerance is 0.3, our max is 20.2, our min is 19.8. Point 3, 20.2, 19.8, and we get our value. And that's the end of our stack. So we go down here, we see a max 2.3, min 1.2. And it's just that easy. So that's what that LMC and virtual condition is all about. That's how we use it. That's where we use it. Well, that brings us to the end of the stacks that we do, kinds of stacks that we do. So let's talk about the Stacks Wizard. And it says you can purchase the Stacks Wizard for $25. The previous version of the Stacks Wizard that was in standalone Visual Basic, they used to charge $100 for it. This one, give you a really good deal. It's only $25. Now, if you hire Dimensional Consulting to teach a Tolerance Stacks class, each student will receive a copy of the Stacks Wizard for free. So I really encourage you to contact me and ask me for a quote and have me come in and teach a Stacks class. I also teach fundamentals of GD&T. I'll be happy to do that too. For more information about that, visit the Dimensional Consulting website at www.dimensionalconsulting.com, and you can contact me directly at dave@dimensionalconsulting.com. So I hope I will hear from you. I will hope you will be able to use the Stacks Wizard and get very good use out of it. And thank you for your time.